Okay, so yesterday I started this and I realized it's not worth putting it into the notes for yesterday. I will put it into the notes for today. All of the vibration notes are completed and you should be able to get access to them now on Quarkus. So in terms of Newton's second law, that's the entire course. So if you want to know what you've studied for the entire term, this is it. Sum of forces equals mass times acceleration, force and acceleration. Force, velocity, and displacement when work energy, and mv dv ds, and force equals m dv dt. The only thing we did for the last 6 lectures was cover force is equal to mx double dot. Now this one uses a slightly older one, a version of the unit vectors, which I don't know why. There's a, oh. Okay. So U is E in these equations, but you have done enough in terms of coordinate systems, I, J, and K. R is equal to Rxi, Y, Ryj, Rzk, and you can write it as x, y, and z, but also as vx, vy, vz for v and a, ax, a, y. Acceleration, the main thing is to recognize that you're dealing with tangential and normal components and recognize how to sort of pull those out. You also, finally, the more complex, and the one that kind of ends up being a little bit tricky because normal tangential, you only look at the magnitude along the path. Here, you have to define everything. So it's really important that when you look at both R, or VR and V theta, it's R dot, R theta dot, and AR, A theta are more complex expressions than that. Projectile motion, we just took the idea of constant accelerations, and from those constant accelerations, we derived a set of equations. The first two come pretty easily. V equals V naught ACT, S equals S naught V naught T plus 1/2 ACT squared. The last one is derived by recognizing that you can make a substitution for dt in terms of ds over v. V squared equals V naught squared plus twice AC S minus S naught. For G and projectile motion generally, yeah, Vy, V naught y, G, T, y in terms of the initial velocity, the constant acceleration, and then in position. The only thing is that when you're dealing with x, or the horizontal component, you don't have an acceleration in that direction, and you need to recognize that and remember it. Absolute dependent motion, you've already done enough again on this. You need to be able to recognize what size or what lengths of a chord change and what lengths do not. There are a lot of different ways of approaching it. I just find this is easiest, making sure that you write out all of the constants. So the sections that are written in light blue on this figure are constant lengths, and you'll notice I end up with 2SA plus SB equals length total, and then everything sort of pops out. For particles, we didn't have to worry about rotation. So you ended up with sum of forces is MAX, MAY, MAZ, or X double dot, Y double dot, Z double dot. If you have tangential and normal components, mass times acceleration tangential, mass times acceleration normal, and m dv dt and mv squared over rho, by using the substituting in the definitions, this deals with the change in the magnitude of velocity, this change deals with the change in direction. As you go through all of these problems, make sure that you recognize what you're dealing with. And so, for example, when dealing with R theta, you don't write, inevitably on an exam, people write m r double dot and stop, and m theta double dot and stop. In both cases, those are wrong. Make sure that you have written down in your crib sheet, and now's the time to write in that crib sheet what you need to know for the exam next week. generally we don't deal with three-dimensional motion, and so it's a bit underlined. Please, please, please stop using our diagrams and make your own. This is, I really think if you do that, it will help you a great deal in getting through this course. If you can draw your own diagrams, if you can understand how those diagrams are set up, and doing it yourself often helps a great deal in solving things. So for example, here, understanding why you would define an X and a Y and the force of friction as it's shown here, and taking care of mg. And always recognizing that g is going down, and your coordinate system then is the only ones that you have to worry about. So then wy, wx, or mgx. I don't know why I did it as w. I hate w. Okay. Work energy. You can write conservation of energy, T1 plus work 1 to 2, T2. This form right here includes conservative forms, and I have repeatedly screamed about this and said don't do it that way. Use instead position 1, position 2, and solve through for everything that you need that is not conservative with work. So here, kinetic energy, kinetic energy. This is spring and gravitational potential. And then this becomes very easily work of friction. When you go into momentum, you end up with vector expression. So work energy is, to a large extent, you may not agree with me, the easiest part of the course, because you don't have to worry about direction. You worry about magnitudes. Both acceleration and momentum, so second law directly, and momentum depends on direction. So drawing things out is very helpful to you in solving out all of these problems. Make sure, and again, this is sort of a useful thing to keep in mind, keep your units. Write your units as you're solving the problem, Newton seconds, and then it becomes a lot clearer when you miss something in your expression. This is one of the hardest concepts in the course. Even after everything else we've done in this course, I think angular momentum is the hardest thing to really wrap your head around. And that is section 3C of, 3C and 4C of the text. And it's really hard to visualize rotation, and a lot of people still have problems with it. I see it on Piazza regularly. But do a couple examples, get more comfortable with it, make sure that you know what's going on, and recognize that largely, unless something weird is happening, there are no external moments, and often you can solve this in this form right here. Okay, what are you doing? All right. When we solve these problems, we break them up into components. And that's why drawing these out is really important. So you often have problems that are linear and angular impulse momenta. So you solve for all of the linear terms in the x, y direction. Then you solve about the k sort of unit vector for angular impulse momenta. And you're seeing these nice videos of me because I was trying to do an introduction to the video that actually this is all based on. And by the way, there is a video for this already. So there is a course summary video that you have access to from this week, and there's a link in the OneNote which I will share later today, I think, or tomorrow morning. So that was all the particle stuff. You know, that was sort of the dream before reading week, and now we have switched over from reading week. We're from reading week into this. And so as you're going forward, we started to look at things that have dimension. And so we have the same sort of terms. You see, nothing really changed there. This is translation. You have position, velocity, and acceleration, rx, ry, rz, xy, Vx, Vy, Ax, Ay. Honestly, we never really do anything in the third component, except for the rotation. And with rotation, one of the things that's still kind of hard, and people are sticking, trying to stick their head or wrap their head around again, is what's the difference with angular motion versus translational linear motion? And there's none. There really is none. The only thing that changes is that the units that you're interested in are thetas. So things displace in theta, they have acceleration in theta, they have velocities in terms of theta. But all of the relationships that you came up with before, like omega d theta, look exactly the same as v dv dx. And if you sort of accept that premise, it's a lot easier to deal with rotational motion. Velocity, all of the chapter 5 problems, and I know that in some of the problems you're supposed to do instantaneous centers or you're told how to do things. If you look, there's a video I do comparing graphical versus vector approaches. If you look at that and you convince yourself, you'll find, I think, vector approaches are a lot more, a lot easier to sort of understand and follow because you only look at the geometry. Instantaneous centers, graphical approaches, both depend on knowing what the motion is. And if you don't know what the motion is, often this gets lost. But this term right here, because it's planar, I've written it sort of in the full form, is minus omega squared r. And it always is minus omega squared r. So you're going to end up with acceleration alpha cross r minus omega squared r for rotation. And finally, you have general plane motion where you have both rotation and translation. And the trick with this, and if I have time, I'll try, and I probably will, I'm going to try and go over the 2022 final exam and do a couple examples that I think are worthwhile. All you're doing with all of the general plane motion velocity is to rewrite everything in terms of translation and a rotation. Translation is just whatever point you're referencing against, and because this is a rigid body, everything stays with the same omega and the same alpha. So r omega, omega cross r. I don't know why I write it this way. So what I should write here is minus omega squared r, where the vector is going to be determined only by planar motion. This is only true because in this course nothing happens outside of the plane of the board. If you're lucky enough and you take a robotics course in third year, fourth year, you'll get an opportunity to apply these same relationships, but suddenly things won't work out quite the same way. So please don't tell whoever's your instructor at the time, we were told in first year it was okay to just do the simplification. It doesn't work in that case. Normal acceleration, lots of different ways, but yeah, there it is. It's always going to end up being this in our course. Planar motion only happens in this direction, and you just solve this for normal acceleration. Everything else, and the reference term here, acceleration A equals acceleration B alpha, A relative to B alpha cross r omega squared r. I didn't put vectors on those terms, but it doesn't really matter. What do you need to know? You need to know parallel axis theorem. You absolutely need to know parallel axis theorem and understand how it's going to be used, and that it has a physical basis. If everything is moving with the same sort of conditions, but sometimes, and there's a problem on Piazza where an object is dropping, or it was a chord cut, 667. A person hasn't sort of responded yet, so I don't know what exactly they did, but if you look at it, the point where the chord connects to the rod is moving, and so the parallel axis theorem doesn't work. And I suspect that was the problem in the solution they chose to use. Now, radius of gyration, another thing you must know. You must know radius of gyration. And again, it's really simply, I've got a really complex shape, and you will see problems using radius of gyration. It's a great way for us to put a question on a final exam with a spool, with some sort of odd geometry, and then say, hey, you have a radius of gyration of this, and then let you solve the rest of it. You use it to deal with, no, that didn't get copied over. All right, so there's a slender rod and a disk, and that's the typical case. Here's the disk, here's the rod. You add them both up, you find out what the center of mass of the system is by just finding x and y, because again, nothing happens in the z direction. But the moment of inertia about the pin is 1/12 mr L squared, mr L over 2 squared, plus mass of the disk, 1/2 r squared, mass of the disk, r plus L squared. If you take that expression, you should know where the 1/12 comes from. You should know the 1/2. We do expect you to know these shapes. But we wouldn't expect you to know what the moment of inertia is without this for that complex or compound body. You dealt with rigid body kinematics, or kinetics, so that was kinematics, this is kinetics. Sum of forces in x, sum of forces in y, sum of moments about g. Sum of forces in the normal direction, sum of forces tangential, and sum of moments is equal to 0 when you have a body in translation. It's not moving, it's just it's translating. So rigid body, the pen is sort of moving across here like this, and it's not moving like this. However, if you look at another point on the body, not the center of mass, everything falls apart. So if you have sum of moments about A, you're going to have this right here, and you have to calculate the moment caused by the perpendicular distance of G to A. So that's a great figure, too. I'm really pleased with that one. Curvilinear translation, the only thing that changes is that you use normal and tangential components. So normal tangential components become very important. We do moments, we got forces acting on there. And you have to know, again, in towards the center of curvature and tangential to the path. And some moments about A, again, are going to depend on how A is oriented with respect to the center of mass. So sum of forces in the normal direction for rotation, you have sum of forces mass times AGN, sum of forces tangential MRG alpha, sum of moments about G, IG alpha, or, and what you have often done in these cases, take it about the point of rotation. That gets rid of everything, but it doesn't really, it's not funny math. This is physics. AT is RG alpha, and the distance is RG, and that also looks exactly like the parallel axis theorem. So if you don't want to use the parallel axis theorem, which I don't understand why you wouldn't, you still have the capability of solving through for these problems. You should get the same result. General plane motion, you do everything about the center of mass, sum of forces in x, sum of forces in y, and sum of moments about g. And you'll notice that in the latter half of the course, we largely dumped all of the other coordinate systems. We haven't done very much with r, theta particularly, some nt. But even when we dealt with nt, we sort of said, hey, this is something that can be described in x, y. And we oriented the coordinate system so it was x, y, but it was nt coordinate, or accelerations in those directions. Translation for work energy, T equals 1/2 mvg squared. Everything is with respect to the center of mass. Parallel axis theorem, same thing. For rotation, you can calculate T, the kinetic energy of the center of mass. It's 1/2 times mass times the velocity of the center of mass plus 1/2 Ig times omega, the rotation. Or, and what we've done over and over, is to shift everything with the parallel axis theorem from G to O, and in that way solve for 1/2 I naught omega squared. Both of these tell you the same thing. And this is something that if you're still sort of struggling with, do problems like this and convince yourself it's true. So as long as you can do that, you're fine. If you look at general plane motion, you will always do things with respect to the center of mass, and you have Ig omega squared. So everything is there. But one of the things to remember is everything is with respect to force, velocity, and distance. And you consider both when you do rotation. So here you have a rotation of a body about point O, you have a body slipping along the surface. But one question that I will keep getting no matter how many years I teach this course, when you have rolling without slip, friction does no work. And then, if you look at the work of a couple moment, then you have, you also have, say, a normal force that's acting through G towards O, towards the center of rotation, or you have force of the pin. Both of those don't do work either. But really, the one that's the hardest to sort of wrap your head around, to sort of accept, is that despite the fact that the wheel is rolling along and moving, the point of contact has zero velocity, and the friction does not displace. Use the second form of the equation that I'm showing you here. I have to write the top one because it's combined, you know, that's what you're sort of told is conservation of energy. But really, when you're dealing with conservative forces, it's easier to write T1 plus V1 plus work 1 to 2. Some slides to update. 1, 2 is equal to T2 plus V2. And the second slide sort of does that. Okay. Not much to say here. I mean, you can sort of look at the summary video if you want the sort of discussion on this. But basically, things that move from position 1 to position 2, as long as you define a datum, you are fine. Once you don't have a datum in place, everything becomes very difficult. So, for example, in both of these cases, they have the same, they've been stretched by delta x or compressed by delta x. The potential energy in the spring in both of those cases is the same whether stretched or compressed by a distance delta x because it's a squared term. Momentum, again, momentum tends to be the hard part in this course. So linear momentum, L equals mvg. For translation, hg equals 0. For the case of rotation, you can do it about point G or about point O. In both of those cases, you're still going to calculate. So if you do the shift and you use the parallel axis theorem, or you look at what your terms are, you get the same result. And for a general case, so general plane motion, you will have L equals mvg, hg equals ig omega. So really, in the end, we get three equations: x momentum, y momentum, and the angular momentum of a system. And so the yellow are the linear momentum terms, the blue is the angular momentum terms. So finally, what we've covered in the last 2 weeks, 2.5 weeks. Free vibrations. So acceleration is proportional to displacement. You end up with a set of equations. And the important thing here is that this term always ends up being positive when you write your final equation. Your equation of motion is always x double dot plus omega n squared times x is equal to 0, and omega n, in this particular case, is square root of k over m. But whatever term you have in front of this x term in free vibration is your natural circular frequency. Yeah. Yeah, hey, there we go. Natural circular frequency, natural frequency. Ignore the Hibbler for now. That's, again, I was trying to deal with, I think I started these in, well, we switched books at one point in this course. Solving these problems, typically you have an initial displacement, and often you have an initial zero velocity. It starts from rest and it's displaced to distance x. And by the way, we want you to solve for this. And you can solve for it by just putting the terms together. Once you do that, you have x, xm, you have the amplitude, you have the phase difference, you have the natural frequency, and you have the period. Yeah, natural frequency. Or frequency, yeah, natural frequency. Excellent. So I did the right thing. Remember that in the case of free vibration, there is nothing to ever dampen the amplitude of the motion. And so if I go from cycle 1 to cycle 2, the amplitude does not change. It doesn't increase, it doesn't decrease. And my solution can be written out as a circle, which is made up of A and B, and based on omega n. Or I can use phi or psi. I think it's psi in that case. When you have force vibration, all you do is you add another term. You have a complementary and a particular solution. And when you have the complementary and particular solution, you have to solve through for everything. Everything sort of goes through. This is still omega n squared. This is the amplitude of the vibration. And you can use that eventually to calculate the magnification effect. The magnification factor is kind of the important term there, 1 over 1 minus omega n squared. That's about all I want to say about that. Oh, and the other thing is, this part right here is the complementary solution. This part right here is the particular solution. And the particular solution is referred to often as the steady state solution. So amplitude, so that's from Merriam and Craig. Magnification factor goes as 1 minus omega over omega n squared, and then you can immediately recognize that you have problems once your forcing frequency matches the natural frequency of the system. Hopefully, if you remember, I mentioned this video on YouTube where this person was looking at coffee and how to grab a coffee as she walked along the road and what was the best way. And she determined you shouldn't hold it like this. You had to kind of claw it or walk in reverse. It's kind of a neat video to see. If omega is less than omega n, m is positive and vibration is in phase with the force. If omega is less than or greater than omega n, m is negative and vibration is out of phase with the force. And this is just amplitude. So if you kind of plotted it in terms of magnitude, it would kind of rise, fall. Damp free vibration, that was the last sort of important section that we covered. We kind of go back, we define a zeta term. Zeta is really useful because it gives you sort of the bounds of the solution. And so you'll see sort of a variation of solutions, but really the important thing here is that zeta is essentially C over critical damping coefficient. You have a standard look to the roots of the characteristic equation. The general equation looks like this, and you can solve through for terms there. And if you look at yesterday's lecture, then you'll see the same thing. So overdamped, zeta is greater than 1. Your solution is x equals AE lambda 1t plus BE lambda 2t. Critically damped, zeta equals 1. And because both of these are lambda 1 and lambda 2 are the same, you get A plus BT e to the minus omega nt. That critically damped case will be one where you have the fastest diminishment in the vibration. And again, you'll notice that it sort of goes off in sort of a similar profile. Underdamped, zeta is less than 1, and we've done a number of cases in lecture on that, and again, I kind of would encourage you to go over those. Make sure that in that case, you notice, I probably should have passed zeta omega n there, but omega n, but only omega d appears here, because in those cases, there is a motion. Zeta is equal to c over 2m omega n. That's the only thing you really need to know about Hibbeler. Viscous damped free vibration. The only thing that is important out of this is the definition. So period of vibration is 2 pi over omega d. Omega d is omega n times 1 minus zeta squared. You can also define something called the log decrement, which is 2 pi zeta over square root of 1 minus zeta squared. Strategies, strategies, strategies. I feel like I need to repeat this and sort of yell it, and probably should yell it at the beginning of the final exam. Draw your own diagrams. It really does help you. And if you're doing this for the first time and you're sort of facing all of these questions, make sure that you do have a set of diagrams written so that you know what you're doing. The other thing too is to look at units. Write your units as you solve the problem. Often one of the problems that come out when we don't do a lot with English units, but inevitably I'll be asked, why is this division by 12 or multiplication by 12 occurring? And it's understanding that English units are 12 inches to the foot. But with SI units, if we give you meters, we may want kilometers. So, you know, it's an easy translation, but make sure that you recognize where it is. I'm going to have time to do at least one of the examples, and I wanted to because of rigid body motion. You always look for the simplest motions to look at. You do not solve for example, the omega of the general plane motion. You inevitably have a simple rotation or translation from which to work from, and that's what you're going to do. Write your equations. Make sure you write down what you mean, and you know, if you want to make sort of an argument that you understood the problem, it really helps when you do that. Solve, review the solution, does it make physical sense? And this is particularly important with vector solutions for rigid body motion. Because with rigid body motion, one of the things that's really hard for you to do, and it's hard for me, is to understand how the motion occurs. And so it's helpful to just draw out the vectors at the very end and say, here's the vector for this side, oh, that makes sense. Or it doesn't, because I'm trying to bend this thing, you know, in the middle. All right, that is everything I wanted to say about the course. Questions? Well, that was easy then. So this is a good one to start with, all right? And the reason why I sort of ended on the point that make a choice about the simplest kind of motion, if I look at this problem before I've even read it, before I read this problem, the first thing I do is I look and say, I don't want to solve for anything on BD in this case. Because with BD, I don't know anything. But I know AB is rotating, and I know ED, DE, the disk, is also rotating. So both of those points will be a lot easier for me to do the analysis from in order to extract out what's happening with the link BD. So I'm not going to solve. I'll write my equations in a form that makes everything a lot easier. So anyway, instant shown, bar AB is in the vertical position and has an angular velocity of 10 rads per second counterclockwise. So counterclockwise, whoop, like that, omega, and is slowing down at that rate. And I draw that. Now, again, I kind of told you, draw your own. But you can put it on the figure at that point just to sort of start things off. bar BD is which can rotate about fixed point E. Okay. Now typically you need, let me see if I put down the questions for myself. Find the acceleration of point B. So I got point B right here. So the first point, or first part, so if I do that, I can solve, let me see how I did this. I can solve and say, well, omega BD is, oh sorry. Velocity of B equals length of AB times omega AB. And I'm given that information at the very beginning of the problem. So when I sort of solve through for it, I can cheat a little bit. I've drawn it out here so that I know velocity B is going to be acting in that sense. And that will equal, when I put numbers in, 2 meters per second. And by the way, all of the videos from 2021 onward, or all of the solutions, or maybe 2020, are available online. And so if you want to look at the summary video for that. So it's the same discussion. Now, okay, I really hate the solution. I shouldn't have done it this way, but there we go. So velocity of D, or B, is going to be acting in this direction. Now, I can visualize this problem. You probably can too at this point. I'm pushing in this direction, so I expect to have a clockwise rotation. So if I have a clockwise rotation, it's acting downward. So velocity of D is equal to, or is acting like this. So if I have both of those, I can say that there is an instantaneous center of 0 velocity at point C. Now this is a particularly easy one because I can just draw that. It's a nice right triangle. Everything works out really well. So if I do that, I can solve through and I can calculate it. Again, I really would recommend, I mean, we forced you in this case to use, to not use vector approaches, but I would still say you'd be better off with it. Now, I know that no matter how I do this, the distance from here to here is 0.25 meters. I know, I think I know, yeah, oh, I'm given 0.25 meters right there. And so that gives me 8 rads per second for omega BD. At this point, I know everything there is to know about this object. So the rigid body has to have the same angular velocity at every point. So if I choose another point somewhere off and do everything with reference to that, it would still be 8 rads per second. Velocity of point D then is equal to LCE omega BD, which is equal to 4.8 meters per second downward. Now, it's not a vector solution, and in fact, what I would recommend is if you do this on your own, do it as a vector, and you'll see how it sort of works out. You don't need to know anything, except, sorry, the one advantage, maybe I should give the one advantage of ICs, is that I know what the direction of rotation is. It's clockwise. And I know what its direction is because I can draw the two and then say, okay, how is this going to actually work out nicely? All right. So velocity of d, so now I have omega of BD. I need to know omega of DE. Omega of DE has to have the same linear velocity at that point. So omega of DE, VD over LDE, and that's equal to 4.8 meters per second, all over 0.2 meters, the radius of the disk, which equals 24 rads per second. And that is clockwise. So I have from that pretty quickly all of the terms that I need and all of the expressions for these terms. Now, I'm given at the very beginning of the problem alpha AB equals 2 rads per second squared, and omega AB equals, yep, I think I gave a weird coordinate, 10 rads, I'm just going to say 10 rads per second, and one is rotating like this and the other is rotating like this. Now, if I put everything together, acceleration of B, equals acceleration of A plus alpha AB crossed with a negative 0.2 J minus omega AB squared RAB. So the acceleration of B I can calculate based on all of this. I have all of the information given to me at the beginning of the problem, and acceleration of A, alpha AB, and omega AB squared. And if I put those together into the vector expression, which is a much better way to do this, I end up with minus 0.4 meters per second squared, I, plus 20 meters per second squared, J. So it kind of makes sense. This thing is sort of down, AB, and that's pointing in the direction of the center of rotation, which is good, so that's J. And then it's going this way, so it's decelerating. All right, that kind of works, and it's kind of sensible. Acceleration of D equals to acceleration of B plus alpha BD crossed with RD with respect to B minus omega AB squared, BD squared, R BD, I think and if you, oh, okay, good, I didn't do that wrong. If you put the terms in, you end up with acceleration of D, which is equal to minus 38.8 plus 0.25 alpha BD meters per second squared in the I direction, plus 36 plus 0.6 alpha BD meters per second squared in the J direction. Acceleration of D is also equal to acceleration of E plus alpha DE cross with RD with respect to E minus omega DE squared RD with respect to E. Okay, that's a lot of things to write. And what I'm doing here is I'm saying, hey, when I look at this, the acceleration at this point, D, is going to be the same on the link BD and on the disk DE. And the advantage is that DE, or E, is clearly not moving, so that has no translational component. And I end up with two expressions, one for I and one for J. And that term ends up being minus 115.2 meters per second squared equals minus 38.8 meters per second squared plus 0.25 alpha BD, 0.2 alpha DE equals 36 plus 0.6 alpha BD. From that, if you just solve the two equations, alpha B, oh, that's not good, BD, which one's it? BD, DE. You end up with 305.6. And it's good to write units, and K, and 736.8 rads per second squared K. And both of those are clockwise. As you're solving these problems, as you're going through a lot of stuff, one, I know there's alternate approaches to dealing with acceleration, and frankly, I will never ever recommend to you to ever do a graphical approach because it is far too complex in terms of the motion and keeping track of things. If you look online, I have put together a summary video where I do a couple crazy examples. I mean, I think that you'll see sort of multiple rods attached, and if you do it with a vector approach, it's not bad. You actually get really good results out of it. If you tried it graphically, good luck. You cannot do it. I cannot do it. I won't even try it. But if you do it this way, often the problems become a lot easier. Now, I did rush through a lot of this because we are at 3 minutes left. But I think one of the things that's really important, and again, there's a summary video where I go through this whole exam, every question on this exam. So just as a reminder, I'm sure you're starting to look at these. This was the second question. This is a nice question, and it deals with rolling with and or without slip. And so here you kind of see a spool. You'll notice that we give you the radius of gyration. We give you a couple dimensions, all sorts of things, and a tension is applied and all sorts of things that you need to do. This is the kinetics problem. The previous one was a kinematics. If you continue with the exam, and you should, this is a question that keeps popping up. How do you do a problem where you have a ball rolling along the floor and the ball is slipping initially and then eventually becomes rolling without slip? This is a great problem for you to look at. Now, the other thing too is you'll notice that in this particular problem we did not expect you to know the moment of inertia. So this is not it's not a disk. It's a sphere. We give you the equation for the sphere in this particular case. And when we do that, and it's with the spool. So this is how we help you. We're telling you things on the exam, and we are really trying to help you by giving you this information. G is given, all of that. It's a work energy plus, I think there was a work energy part with this, but no, there's not. It just goes straight down. This is a fun one. And again, all of this stuff is available to you online. And if you're starting to decide what to look at, start with the newer exams before you go to the older ones. The important thing in all of this stuff, especially when you get to the kinetics and the vibration, make sure that you are able to draw these figures. You need, if you try and draw that figure on the exam paper using our figure, it really isn't enough room to think about it. But if you do it on your own and just sort of draw a circle and add a mass and say, okay, that will work, it makes a lot more sense and it's a lot easier.